Alright, sorry that last video was a little bit low energy, but here we are to talk about motion and torsion in space. Motion in space is something you should feel fairly confident about. We do have a little bit of something interesting here with our clank that we'll talk about. But really, the main focus is just acceleration, velocity. But the thing is, acceleration can move in more directions than you originally expected. I'm not going to get ahead of myself. Let's do a little bit of math here, folks. To go from position to velocity, I take my derivative. V of t, which we would also call r prime of t. Well, that thing is it's just three separate derivatives. 3t squared in the I direction, 2t in the j direction. Ta-da. How would I find speed? We know that speed is the magnitude of r prime. A lot of people think of absolute value. Absolute value means distance from 0. The magnitude is the distance from 0. It's the same exact concept, but generally kids just think, hey, I just flip it and make it positive. That's not quite the case. You're thinking, how strong is my motion away from the center? Like if I have a vector and I take the magnitude, all that's left is the strength and none of the direction. So that's what we're doing. We're taking the strength of the change in position over time and removing the direction from it. Again, that's going to be 3t squared plus 2t squared. Sorry, 2t squared. Where's my head at? All right, and also it asks us to please evaluate at t equals 1. So I also probably should have done, hey, v of 1 is 3 comma 2, right? Switching between forms there a little bit, so it's not a huge surprise that the speed at 1 is going to be the square root of 3 squared plus 2 squared, which is rad 13. All right, nothing too crazy there. All things that are within your world. Even if I went down to acceleration, we know that acceleration would be 6ti plus 2j. And again, a of 1 would just be 6 comma 2. All right, even this one, now it's starting from the other end. It gives me acceleration and says integrate your way back to position. This one is just a tiny bit more tricky than the others. Not anything too crazy because the integral of acceleration still gives me velocity. So when I do this antiderivative, 2t squared in my I direction, 3t squared in my j direction, and a t in my k direction. But the issue that kind of comes up is, hey, I need constants, right? This is not a definite integral. I need constants, and guess what? It gives me a nice initial condition. This is probably the wrong way to write it, but honestly, that's how I do it, right? I'm going to have 3 separate constants in 3 separate directions because they have 1, 2, 3 separate initial conditions. And so, yeah, I would plug in v of 0 is 0 plus c1, 0 plus c2, 0 plus c3. You know it's not always 0, but since these are just polynomials at 0, they make 0. If it was something like trig or a natural log, I'd probably get something a little bit more exotic out of this guy. But really, v of 0 just tells me that the constants are equal to c1 equals 1, c2 equals negative 1, c3 equals 1. So it's 1, negative 1, 1 up here. So now I'd have my full velocity vector, 2t squared plus 1, 3t squared minus 1, t plus 1. And I would repeat this again one more time to go from velocity to position. Again, the integral of velocity is position. And so I'll do that over here. R of t is just going to be 2/3 t cubed plus t. That would be t cubed minus t. This would be 1/2 t squared plus t. And don't forget, like plus c4 plus c5 plus c6. I'm not going to call them 1, 2, 3 because that, mathematically incorrect. And again, using this initial condition, 1, 0, 0. Switching between forms here because it's healthy and good for you. That means my final function, r of t, is going to be 2/3 t cubed plus t plus 1, t cubed minus t plus none, 1/2 t squared plus t plus none. And that's it. right? There's no reason to drag this half of the sheet out. The back half is where it gets a little bit interesting because we have a formula to derive. And I want to take a minute to do this with you. Normal direction acceleration finds the change in t. How tricky that might feel, because my normal n is the derivative of t. This is kind of one concept that'll help us a little bit as we keep going through. R prime velocity is most closely related to t, where r double prime is most closely related to the second derivative, n. Now, I know that n, I should probably just say like approximates. N is t prime, but it's normalized. So that normalization makes it so these two things aren't directly equal, but the concept still holds that velocity is mainly going to come in my tangential layer and acceleration is mainly going to come in my normal layer. But as we'll see in this formula and these formulas, there's actually a little bit more to it, right? This is a dot product. This is taking my second derivative and dotting it with t. How interesting. So how much is my second derivative going in the t direction? I'm getting ahead of myself. Let's do the good part. Let's do the good part. So we have a proof to build out here. So please just follow along a little with me. I'm just going to use formulas we already have. Things like t is r prime divided by magnitude of r prime. Well, we know r prime is v of t, velocity, where this would be the magnitude of the velocity. So t is actually velocity divided by speed. Now, technically, velocity is v, and speed is like this fancy v. But with my handwriting, they look far too familiar. So, similar. So this v down here is actually speed. All right, let's use this. That means that if I multiplied this across, velocity would be speed times t. Well, let's take a derivative so I can get to my acceleration. Well, because this is a product, I would have to use the product rule. Speed is a variable. T has variable, so variable value. So I would have to product rule this. I'm going to call that speed prime times t plus speed times t prime. All right, let's tackle this speed times t prime, because there's some stuff baked in here. We already said speed prime times t kind of already gives me that acceleration. How much of my acceleration is going in the direction of t? This is my t direction. But you know when you drive in the car with your mom, she slam on the brake, you go forward. She hit the gas, you go back. But there's another force that you feel while you drive in the car, and that's hitting the corner really hard is going to send you side to side. It's going to send you in that normal direction. I have these notes still sitting over here, right? If this is the direction of my car, the speed is forcing me this direction, but that turn is pulling me in the normal direction, t, n. It's going to happen right here, speed prime times t. Let's go find, sorry, it's going to happen over here. Let's go break down this speed and especially this t prime and figure out what it is. Well, t prime is part of n. N is t prime over magnitude t prime. So that would just tell me that t prime is n times magnitude of t prime. All right, well, we'll bake that into this layer as we still have speed prime times t plus, now my t prime is going to get replaced, speed times n dot magnitude of t prime. Let's take it one step further. One step further actually comes from my curvature. My curvature is t prime over r prime. It's my change in t versus my change in s, my change in curve length. And my change in arc length or curve length is the integral of this derivative. So what this tells me is that magnitude t prime could also be written as curvature times speed. So when I bring this over, again, one more time, adding it to over here, my final calculation for what speed is the change in speed in my t direction plus, this is going to be speed. Sorry, this is curvature times speed. So I would have speed squared times curvature dotted with n. This is a scalar. This is a scalar. So it's just telling me the strength of that n-word, n-directional acceleration. This is telling me the strength of my t-directional acceleration. So my total acceleration comes from that combination. A scalar times a direction plus a scalar times a direction. Again, I hope that you followed a little bit. You can see where these come in. This thing is a of t. This whole thing is a of n. This whole thing is a of t. And yes, it gets dotted with t and dotted with n to become scalars. So my total acceleration is just a number. But realize that's where these formulas that you see here and here come from. Let's use it just a little bit. A particle with this, find an and at. So I need to find first derivative. I need to find second derivative. Quick. Nice. Now I'm going to do the cross product over here. Right, this thing is actually set up as a vector, like a matrix already. So I'm really just covering and multiplying. You know, cover your I, do your determinant. Cover your J. Sorry, the camera is a little funny here. Cover my J, do my determinant. Cover my K, do my determinant. And when I do that cross product, I hope you trust me, we end up with 6t squared, comma 6t, comma 2. I also need, notice, these are scalars. This is the amount of acceleration in this direction. That's F equals ma. That's force. That's a scalar number. T gives the direction. N gives the direction. So I need to turn this into a scalar. I need to magnitude this thing. Ta-da! It's not glamorous, but it's good stuff. In the same way that I need to get r prime, this magnitude, from up here. Easy peasy. Like doing these, it's just a formula problem. This is where the formula comes from. This is where the comprehension comes from. Hey, this is my acceleration in the t-word direction. This is, you know, speed times t prime. This is speed squared curvature in the n-word direction. So here we go. Let's put it all together. A t is formula. Dot these things. Dot these together. 4t. 18t cubed. My denominator, this thing. 1 plus 4t squared plus 9t to the fourth. An is going to be this. How ugly. Over that same other denominator. It's not nice, it's not glamorous, but it's real. And if I plugged in any t value over the domain of this thing, I would get the acceleration. If I dotted them and added them, I'd end up with a total acceleration, but we're a little less worried about that. Last but not least, there's a third type of acceleration, where I should have deleted this line for us. There's a third type of acceleration, and that's torsion. That's the change in B. And so this is when my roller coaster starts twisting. It starts turning. It's that corkscrew motion. You can't get it in a car because the car is just going left, right, forward, back. We need something that's going to be twisting and diving, like an airplane or a roller coaster track. It's the degree of twisting of the curve. It's how the osculating plane contains N and B. It's how this thing rotates. We have rotational acceleration of the T and B frame. Yep, rotating, accelerating, absolutely. and it only exists in that NB plane. It's pretty absent of t. And all those t things are getting crossed with n. All those first derivatives are getting crossed with second derivatives. So the direction is not with t. It's orthogonal to t. So this is going to be giving me b dot my jerk over kind of a magnitude of b squared. This is where we have a lot of small writing. I hope that you're just going to trust me as I find first, second, third derivative, cross them, dot it all. Let's see how this goes. Yes, I have a cheat sheet in case you were wondering. That means r prime over here is cos t, negative sine t, 1. That means r double prime is negative sine t, negative cos t, 0. I'm sure you can figure out r triple prime somewhere out here. Well, actually, let me do the cross for this first. R prime cross R double prime. We do get an interesting cross here as it goes through. This cross product makes this interesting quantity that I do want to pause for a moment and talk about. That's going to be cos ti negative sine tj minus cosine squared t minus sine squared tk. So what ends up happening here is this negative cosine squared minus sine squared is a negative 1. And if I wanted to magnitude this thing, magnitude r prime cross r double prime, this would give me a 1 and a 1. It'd be cosine squared plus sine squared plus 1. That's rad 2. We have our triple prime somewhere out here. Let's just write it. Not a lot of space for us to work, but I promise a third derivative is not going to kill us. I've got negative cos t, I've got positive sine t, and I've got 0. All right, last but not least, let's start calculating. Let's just throw this all into this formula. R prime cross R double prime is this vector, and I'm going to dot this. Then I got to divide by this magnitude squared. When I dot these, I get a negative cosine squared. I get a negative sine squared, and I get a 0. Well, negative cosine squared minus sine squared, that's just negative 1 over 2. My torsion on this whole thing, the amount of twist, the amount of acceleration in that direction is always negative 1/2, absent of where I am on the track. I hope this gave you a new perspective on motion in 3D.